Hello everyone. Today we are going to solve yesterday's daily problem because yesterday I was little bit of busy, so I have not solved that problem. So let's see that. If you go to the problems section and you will see a calendar here, like you can see this was yesterday's daily problem. So let's see what was that. Uh, it's a medium problem. Basically, we can see problem number 3629. Minimum jumps to reach end via prime teleportation. Okay, so I am also like reading this question for the first time, so I also will tell you what where my thoughts, like what I am going to thought about these, what will be my what I will notice in this problem, how will I approach. So I will see, let's read the problem statement. It said that you are given an integer array nums of length n. You start at index 0 and your goal is to reach index n minus 1. Okay. From any index I, sorry, you may perform one of the following operations. First, adjacent step, jump into an index I plus 1 or I minus 1 if the index is within bounds. Okay. And prime teleportation. If numSi is a prime number, you may instantly jump to any index j not equal to I such that nums j mod p equal to 0. Okay. So return the minimum number of jumps required to reach index n minus 1. Okay. So first we just read the problem, and what we get that we are given an array and our target, we will start from index 0 and our target is to reach index n minus 1. Okay. And we have two type of step, adjacent step. We can go I plus 1 or I minus 1 from I. And if the current number is prime, then we can go to any multiple of it. We have to find minimum number of steps. So first we can see that as we can move I plus 1, so we can simply linear travel and we can go in n steps. So mm, not n, basically n minus 1 steps. So the answer will be less than n minus 1, which is like not that much useful in this problem, but I'm just telling that what we are noticing. And other thing, like whenever we found these type of problem, it either be kind of like dynamic programming problem or graph problem. But here it is not dynamic programming. But how we can tell that? Because the graph can, like if you see these things as a graph, like there is a edge from 1 to 2 because there is a path we can go, and from also 2 to there is a edge to 4 and also 6 because we can go, but there may be cycle. So if there is cycle in a graph, we can't apply dynamic programming there. So it will be a any kind of graph problem. So let's find out what will be that. Like here for 1 to 4 6, it is said that we need only two jumps. So if I go to one node and just write 1 2 4 6, so 1 2 4 and 6. So if I apply, like draw the edges from this, like we can go from 1 to 2, 2 to 4, 4 to 6, as well as 6 to 4, 4 to 2 because the edges are bidirectional. And from 2 we can go 4 and also we can go to 6 because 2 is a prime and 4 and 6 are multiples of it. So now from this node we have to find the shortest path to this node. So basically this is a shortest path finding. We have to find the shortest path from first to last node. Here the shortest path length is 2 because we can go from like 1 to 2 and then 2 to 6. So that's why the answer is 2 here. and and you can see in this graph there is cycle, so much cycle, so we can't apply dp here, so we have to find any shortest path finding algorithm to find this. So for that we can use like any graph traversal kind of thing, we can use the priority queue or simple queue for this. But I think if we do only bfs it will work. Like from here I will just go here and then From here, I will put 4 and 6 in the queue, and then as we are finding this, so the answer will be this. And if more numbers are there, then it's like uh, 4 and 6 will be in the queue. Then after we pop 6, we will get 7. So the answer will be 3. So what we are going to do, we are not going to construct any edges, because that might cause so much edges in the graph. But we are going to uh, without creating any edges, we are just simulate the BFS traversal process, and we will find the answer. So let's go here, and here also, like, from 2 we have to find like how many multiples of 2 are there, and we will jump them. So that is like time consuming. If I think there are so many primes and also so many multiples, then we can use a visited array and mark them that this particular number has been already visited, so there is no point to visit this. But still we have to check. So while we will go to check, then also it will take so much time. So what we can do here, like, if I think carefully, like from any number, if I want to find their multiples, it will take a good amount of time. Like, it might be optimized here, but it will take good amount of time. But if I think reverse way, that from instead of going 0 to n minus 1, we will start at n minus 1 and we'll came back to 0, like the same problem. Like the answer will be same, because we are just finding shortest path here. So from this to the last node, the shortest path is same as from last to first node. So what we'll have to do, like the operation, what will be the operation? The operation will be the adjacency operation will be same, that we can go to any adjacent node. And for the prime operation, now instead of jumping to any multiple of a prime, what we can do, we can go to any prime factor of the numbers. Like from 6 there are two prime factor of it, 2 and 3, but here 3 is not present in the array, so we will go to 2. So also we know that number can have at most log n number of primes in it, like as a factor. So it will take less amount of time and we can do that. So these are my observation, like how we can uh, see and find solution of any problem. Like here I found that in a normal way this might take good amount of time, but if we just inverse the problem, and also like we just came back from this node, here we have to just find the prime factors, and then the prime factors are limited, so we have to just hash the like position of the prime factor, and once I utilize any prime factor, I will just mark this prime factor has been already used, so we are not uh, considering this prime factor anymore. So these are my ideas. So like here, if I simulate this in the dry run kind process, what will happen? Like in the queue, first 7 will go there. To reach 7, we need 0 step, because we are starting from here. Now there are only one path there, so path will be same as previous. Now from here we will pop the queue, and then we will get 6 1, because we have node 6 as a neighbor and we need one step to reach there. Then from 6 we will get two neighbors, that is 4 2 and 2 2, because we can reach 4 with 2 step and 2 with 2 step. Then we will pop 4 2, and we have 2 as a neighbor, but as we already have, like, then if we consider this, then there will be 4 3, sorry, 2 3, because from 4 we can reach only 2 at 3 step. But if you see carefully, as we have already reached 2, in less amount of steps, so we won't consider this. So for this, we will just track a visited array that if I ever visited this index, I won't visit it anymore because in the BFS thing, like if I already visited, that means that index has been visited in less steps. So that is optimal already. Now from these two, we will pop this and we will get 1 and like 3. We also will get like 4, 6 as a neighbor, but they are already visited, so we won't consider it. So that's the simple idea. We will just do BFS and we'll find the answer. So in the editor, let's like rename this and we'll find first the size of the array, and then we need to like do a simple BFS. So I will take a queue in queue. Let's take a pair to track the node and the step. Now queue dot push n minus 1 0 because we can reach n minus 1 in 0 step. Also, we need to take a visited array, vector boolean visited n, and we will make this visited of n minus 1 as true. Now, while queue is not empty, we standard by BFS, we will pop a node and step. We can also rename this as index and step, each queue dot front. Now we will pop this. Now we will see that if the index is 0 or not. If the index is 0, that means we have reached our target, we will just return the step. So if this happens, we will just return step. Otherwise, what we are going to do, we will consider all of the neighbor of this current index, and then if they are not visited, we will put this in the queue. So first, there will be three kind of neighbor. One is like I plus 1, like index plus 1 is a neighbor, index minus 1 is a neighbor, and any prime factor of it is a neighbor. So what we will do, we will see if index plus 1 is valid and then not visited index plus 1. Then we will first mark it as true and we'll push in the queue dot push index plus 1 comma step plus 1. Similarly for index minus 1 also, if index minus 1 is uh, greater equal to 0, which is like index is greater than 0, if index is good and index minus 1 is not visited, then we will simply mark index minus 1 and also do the same. So first two things are done, like the simple things. Now for the prime factors, we need to get all the prime factors. So prime factors of like auto prime factors, get factors of array of index. So now what we are doing, where we will just write a function that will return all the prime factor of the current number, and then we have to find the position of that factors and we will jump like consider that nodes also as a neighbor. So for each prime factor, for each prime of prime factors, what we will do, we have to find the position of the those primes. So There also we will use auto positions, uh, or we can say indices. Hmm, let's write this position equal to, we'll write some function like that will return the position of current prime. So you can do everything here, but I prefer to write these things as a function because like it improve your the readability of your code. Like if any other person read your code, he will be able to understand like what you are doing, and also it is very helpful in the debugging phase. Like if anything crashes or breaks, you will be able to like ensure that at least this function is correct, so I don't need to like consider in this, we can check other things. So make your code modular, like make everything as a function, and you can also like reuse those things in other way. So now we got the all the positions. What we can do also, like if you see, we can also optimize like if we already like consider any prime, like for any number we got 2. Now for 2 we will eventually go the all the position of the 2, and we'll consider or calculate something and mark them all. So for other number, when we again find 2, we don't need to actually go every place, every position of the 2 and check that if it is visited or not, because as 2 was founded earlier, so it is, we know that the all the position of 2 are already marked, so there is no need to check all the position of 2 again. So we can use a set here to check that if this prime is already considered or not. If this is already used, then we won't use this anymore. So here we can use a set of used prime. Let's say used prime. So now here, if my set, that is used primes, if used prime dot contains prime, mean current prime, if used prime contain this current prime, then we will do like we will just continue, because we know that all the position of this will be marked, and then we will simply insert this prime, used primes dot insert prime. So after that, we have just treated this, then we will retrieve all the position of this. Now we will simply go over all the position, and if this position is not visited, then we will mark this position as true and also push this in the queue. So queue dot push this position I and step plus 1. So that's all I think. We just need to now, it should work, because like here we are doing this, and also we are taking this step, and we are finding all the factors of any number. Then for all the factor, if that is already used, we are simply ignoring that, and otherwise we are going to retrieve all the position of that, and the which position are not visited already, we will just visit them and we'll push them in the queue. And in last, like this thing will execute after n minus, at most n minus 1 step, we know that. So the code will not reach here, so we can return anything from here. Let's return minus 1 or something. So the code will not reach here any time, to ensure that you can use the assert also. Like what assert do, whenever assert face any false statement, it stops the program and like exit the program and show you a message that this assertion has failed. So the code will, if the code anytime reaches here, this asset fall will like exit the program and will show a error message. And now we have to just write this function get factors and also get position. So for position we can use a map simply. First of all we need to do prime factorization. So we can write the sieve. Also we can use linear sieve here in the CP algorithm like here. CP algorithm website is a good resource you can follow. Like here for every topics you can find so much topics and also with code and also related problem in that. So here you can study about linear sieve. It runs in linear time. Yes. Normal sieve basically take n log n time. Here it is another thing. So I will just going to copy and paste this and let's format this. Here if I see the constant here is 10 to the power 6. So we don't need to do the sieve up to 10 to the power 7. We can do this up to 10 to the power 6 and some couple hundred times. So now this need to be linear sieve. So here we got linear sieve. We will call linear sieve from here. Linear sieve. Now if you see carefully like if I go like call this function so much time like every time it is going to go 10 to the power 6 time. So if in a single run, if this function is called like the min jumps is called so much time for uh, small arrays also, this linear sieve is going to call and this whole thing is going to rerun again. We don't need this actually. We need to compute this only once during a single run. So to ensure that uh, if we instead of like calling this function multiple time, this thing should be computed only once. What we can do, we can use a boolean flag like the global flag in it, let's say in it, so it will indicate that the this thing is initialized or not. So here we can show if it is already in it initialized, then we will simply return. We won't compute this thing again, and after computing we will just make this flag true. So it will ensure like this function will only run once during the whole runtime. So these things are good. Now we need to write this get factors function. So it will return a vector get factors and take a number. Now this LP is basically lowest prime factor of the number, and this PR is like the primes in that range. So you can also use sieve to find the lowest prime or highest prime factor of a function. Sorry, number, and you only need any prime factor of a number to get all the factors, like highest or lowest, anyone. So here, what we'll do, we will just simply use vector result or factors. Now, while n is greater than one, what we will do, we will just take SPF smallest prime factor equal to LP of n. Now, uh, while the number contains that prime factor, we will just divide that with so SPF equal to 0. We will just divide the number with that SPF, and we will push back this here. Push back SPF. and then we will return factors. So what we are doing here, this LP stores lowest prime factor of any number. So while the number is greater than 1, what we can do, and also like what we will do if the number is 1. So if the number is 1, the it will return an empty vector. So that will also good. It won't cause any issue. So we will just finding the smallest prime factor, and then we are taking this and then removing all the occurrence of that prime factor from the number. So that should work. Now we have to write this function get position, which will return all the position of the prime. So we can use a map here, like map of int of vector of int, which will like store all the position of the primes. So prime position, because we can store all the position of the all the numbers, but we don't need. We just only need the position of the prime number. So we can also store the prime numbers position. So we'll go over all the array equal to 0, I less than a, and I plus plus. Now, if the number that is array I, if this is prime, so how can we check if this is prime or not? With this, like we are not storing any boolean vector here. What we do in the standard sim, but here we are storing all the prime. So either we can binary search in this prime that this number is situated or not, that is logarithmic time, but we can do this thing also in constant time because we have stored the lowest prime. So for any prime number, the lowest prime of the number will be it's the number itself. So if the lowest prime of array of I is equal to array of I, that means the number is prime. So then we will store the position of that prime number. So prime number position of array I dot pushback I. Now here we don't need actually any function. We can just call p prime position of that prime. So it will return this as position. So now I think this is good to go. We can run this, like if it is working or not. So it is working fine on the samples. Let's run this on the main test case. Let's see if it is good or not. So it got accepted. So that's all for today. Like you can see like how I thought and approached this problem. So you have to basically break down the problem step by step, and you have to thought which tools you have to complete that particular small task. Like, do you have any tools or you know any technique by which you will able to solve that in good amount of time? So if I also like discuss the time complexity here, this linear C function is linear. Basically, it can go at most 10 to the power 6, which is the as the same order of this kind of. So let's take this as linear, and then here we are finding all the position, which is also like n log n kind of time. We can say because we are using map here. Uh, then in this BFS, as there are at most n nodes, and we are also using this visited array, so we will push at most n nodes in this queue. So this while loop can go at most n times, and here the prime factor will take log n time, and this set will also logarithmic, and this thing we will go logarithmic time. So the overall time complexity will be n log n kind of thing. So overall time complexity is order of n log, like n is the size then log 2 of like the max value kind of thing. Or we are taking constant in here. So, and for the space, we are taking just uh, linear space. So, space complexity will be order of n because we are not just using this kind of visited and this position. Also, a cube which um, can have at most n elements. So that's all for today. Thank you. And also you can see uh, this part of code has never reached because the assertion has not fault. So we will find the answer every time because if you also like thought this with some common sense that there will be always a path because uh, like uh, because of the adjacent system we can always go adjacent and at most n minus one time we will reach to the zero. So that's all for today. Thank you.